All right? So quick example. In the figure, name a pair of complementary angles, a pair of supplementary angles, and a pair of adjacent angles. Looking at that. Couple of complementary angles. Who's got them? Yeah, what you got?
Angle ABC and angle RST.
Okay, angle RST, and I think you said angle ABC. Okay, trace out ABC. Yeah, that's not what you said, though. You said ABC. Right angle. Just got to name it better. ABC would go that way, right? We actually want to do maybe BAC. Okay, good. Just be careful. Just be careful. But yeah, you got the right two angles. Good. Supplementary angles. See them? Talk to you. Tova?
Angle DAC and RST.
Angle DAC. And angle RST. Yep. Ooh, that's bad. Okay. And then just a pair of adjacent angles. Okay, what you got?
CAD
Okay.
and RST. Yeah.
CAD and RST.
TSR.
TSR. Those guys are side by side? Uh-oh. Angle CAD and... Yeah, angle CAB. Those guys are side by side. Okay. CAD and RST are definitely supplementary, just not side by side. Okay. Good. Oh. Okay. How we can use this information, right? Even if we don't have a picture of angles, if we know that two angles are complements of each other, and that's what we can write sometimes. If two angles are complementary, sometimes we'll say the angle this and it complements this other angle. Okay. Well, let me back up here too before I forget, because this example is getting ready to do it. We haven't really talked about it to this point. And I'll do it this way. Okay. There is an alternate way to name angles. Right? This is angle ABC, right? Or angle B. Or if there's like 20 angles in the same diagram, which could definitely happen, what we can do also is make life a little bit easier and just stick a number down in the vertex. And so we can use numbers to name this guy. So we can call this guy angle ABC, angle B, or angle 1. Okay? We'll number the angles. We'll just put a number down in the vertex and use those to name the angles as well. Okay? That's what's going to happen in this next example. Okay? So given that angle 1 complements angle 2, and the measure of angle 1 is 68 degrees, then we can find the measure of angle 2. Should be no problem, right? We know that if they're complements, they have to do what? Add to 90. Okay? So if angle 1 is 68, that means the measure of angle 2 is simply going to be, oh, not 98, 90. Yeah, 22. Okay? So just know that the complementary tells us something. Okay? We still need to see that for a second. Same thing with supplements. If we know that two angles are supplements, that tells us that those two angles add to what? 180. So same thing here. If angle 3 and angle 4 supplement each other, we know they have to add to 180. Okay, so since angle 4 here is 56 degrees, subtract 56. And so the measure of angle 3 is 124. Okay? All right? Carrying on. Okay, we got a little sports example. When viewed from the side, the frame of a ball return net forms a pair of supplementary angles. And it will. If we don't know those angle measures, but we have some expressions, then we should still be able to find the angle measures. Okay? Because looking at these two angles, since they're forming a pair of supplementary angles with the ground, these guys and these guys, then together they make a what? They make a line. Okay? Or, since we're talking about angles, a straight angle, right? So, what do we know about these two angles then? What do we call them?
Supplementary.
Yeah, they're supplementary angles. So, we know that measure of angle BCE and the measure of angle ECD is going to be equal to 180. So we can come up with an equation for us to go solve. Just plug those in. 4x plus 8 plus x plus 2 has to equal 180. And we're off and running. Should be able to get down to the place where, to a point where x is 34. It asks you to find the two angle measures. So of course we're not finished yet. You have to come over here and plug 34 into these two guys. Right? You should be able to get to a point where this is 36 degrees. Okay, which makes this needs to be 124. Nope. Sorry. How about 144? Okay. And a great way to check yourself here is when you actually plug the 34 into the x's, then your two angles better add to 180. If they don't, then something's definitely gone wrong. Okay? All right. Oh, here we go. Some other angle pair relationships that we can come across. Okay, we've already seen one pair. And they're called a linear pair. It says in your own words, write a definition. Those look like pretty good words for your own, so let's use those. Okay? But in your own word, write the definition of a linear pair. There are two adjacent and supplementary angles. Okay? We've already seen these. Okay? Two supplementary adjacent angles form and you guys keep saying a line, and that's great because line is the base of linear. So hopefully it makes sense that if they're a linear pair, then they're two angles that form align. So they're non-sharing sides, they're non-common sides, are opposite rays, or they help form a line. Okay? So you see the examples there. Left-hand side is a linear pair, right-hand side not. They have to be side by side. Okay? Vertical angles, vertical pair. Okay? You have vertical angles in the left-hand picture there, and you do not in the right-hand picture there. And the difference, by definition, is this. They're two angles whose sides form two pairs of opposite rays. Okay? Two angles whose sides form two pairs of opposite rays. Now, a nice, quick, easy way to find vertical pairs is you should be able to, you're looking for any two lines that form a nice X, perfect X. Okay? So that's a pretty nice X. That's an indication that you've got you got vertical pairs. Okay? And the vertical pairs are going to be the ones that are back to back, right? If you trace the angles, they'll form an X. There's another way to look at this too. If you trace angle 7 and angle 6, you'll get that X. So that means that angle 6 and angle 7 are vertical pairs. Oh, by the way, so are 5 and 8. Okay? 5 and 8 are going to be vertical as well. You try to do that with 9 and 10. Doesn't look like any X I've ever seen. Okay? So those don't count. That's why those don't count. Okay? All right. Try to pick them out. Identify all linear pairs and all the vertical angles in the figure at the right. Give you about 10 seconds. Linear pairs. Everybody find a pair? Shout them out. Say it again. 1, 2, and 4. Well, they're pairs, so that suggests we need just 2. Okay? So we need just 2 angles that are going to form a line, right? Okay, good guess. Yep.
4 and 5.
4 and 5 works. 2 angles that are forming a straight line, 4 and 5 definitely do that. Okay. There's another pair. Anybody else see the other one? Yes, ma'am. 1 and. Okay. The issue with 1 and 3 is that they're not side by side. Right? There's a gap in between them. Okay. We can't have that. Yes, ma'am. Yeah, 1 and 4 will. There's not a gap between them, and they still form a straight line, okay? And I know we're not experts yet, guys. It's okay if we're off. These are good things to talk about, okay? But 1 and 3 are not side by side, so we can't use those guys. Although I agree, Lizzie, that they do have 2 sides that form opposite rays, so I know where you're going with that, okay? All right, how about vertical angles? Anybody find vertical angles?
1 and 5.
1 and 5 would definitely be it. Is that what you're looking at, Shelby? 1 and 5 would definitely work. And the only pair in there. Okay? Yeah.
Because these angles are numbered instead of lettered.
Right.
But if you had, say, like the big midpoint is A or whatever,
Mm-hmm.
and then you have the line that's going like that way is B, and the one to the right C. Basically, angle 2 plus B is vertical 4, right?
Yes, yes, yes. That's a good point. And I was going to mention that with linear pairs also. What he's saying is there are kind of some hidden vertical angles in here. There's just not a good way to name them, right? So if you crisscross these two lines, they make an X as well, right? These guys right here. And so this guy and this guy are going to be vertical too, only we don't have a good way to name them. So you're right. Absolutely. And it works for the linear pairs as well. This guy here and this guy here would be a linear pair, but again, no good way to name them. So there are some hidden guys in here. We'll pick that up a little bit more later. But it's a good point. It's a good point. Okay? All right. If two angles form a linear pair, then what do we know about their measures? They have to do what? If two angles form a linear pair, the measures are going to do what? Yeah, they're going to equal 180. So they're supplementary, right? So, quick example here. The measure of one angle is 5 times the measure of the other. Okay? Find the measure of each angle. Well, we know they're going to add to 180 because they form that straight angle, straight line, however you want to look at it. The issue is we don't know what these angles are. We don't know either one of them. So if we let one of them be x, then the other one we can let be, since it's 5 times larger, 5x. Yep, yep. And so we can set it up this way. So 6x is going to equal 180. Okay, so x is going to be 30. That means your two angles. You plug in 30 here, 30 here. Your two angles are going to be 30 and 150. And again, they better add to 180 or something's not gone our way there. Okay? All right? It's there, guys. If you didn't get it all in, it's going to be there in the notes. Okay? Just got to keep moving here. All right, polygons. Talk about classifying polygons. This should go pretty quick. It's not the first time you've seen this. There should be a lot of review for you. Okay, but a polygon is a closed figure in a plane. And there are some criteria in order for a shape to be a polygon. Okay? And the criteria is it's got to be formed by connecting at least 3 line segments. They have to connect at endpoints, and each segment is only allowed to intersect exactly 2 others. It's got to satisfy all those criteria, or it cannot be a polygon. Each line segment we're going to call a side, and as I mentioned before, any corner in geometry, pretty much, we're going to call a vertex. So angles have a vertex, polygons have a vertex, it's just those corners. Okay? And then we can talk about a diagonal. If I gave you a rectangle or a square, my guess is you could draw a diagonal, no problem. Okay? But for any polygon with any number of sides, a diagonal takes on a very specific definition. Okay? And that definition is a segment connecting 2 non-consecutive vertices. Non-consecutive. Consecutive means one after the other, right? Non-consecutive would be not that, okay? So we're looking for vertices that are not right after each other. So if we start here, to draw a diagonal might be a little weird to think about in this polygon. But you start at this vertex, we've got to skip one. And then draw, if we draw a segment to the next vertex, that's a diagonal. Okay? By that definition, is this the only diagonal in there? And the answer to that question is no. There's a bunch. Okay? You start at any you pick any vertex you want. And all you have to do is skip the next one. Okay? So if I wanted to start here, all I have to do is skip this guy. And if I do that, I get these two diagonals here. Because we skip and skip. If that makes sense. Okay? Outside of rectangles, squares, diagonals get a little bit weird looking. Okay? There's diagonal. Okay? Two types of polygons. Polygons can be convex or concave. Convex or concave. And you see the definitions here. I'm going to offer up another way to tell the difference. But a convex polygon is a polygon in which no segment connecting two vertices is outside the polygon. And you'll kind of see what they're talking about here in just a second. Okay, but in a convex polygon, the consecutive vertices share a common side, the consecutive sides share a common vertex, and the consecutive angles share a common side. Okay? And the deal with concave is that it's not convex. There's only two choices as far as the shape goes. We're talking about the shape. Okay, a polygon in which at least one segment connecting two vertices is outside the polygon. Again, it's a nice way to tell, and I'll show you how. But there's another way that I think is maybe even easier, right? So here are some examples of convex polygons. Okay? Convex polygons means that, to me, the definition up here is good, but another definition, another way to tell, is if all these sides for polygons are segments, right? We've talked about that before, or we just talked about that a second ago, right? Everywhere you see a line segment, there's really a line that exists there as well, right? So another way to tell convex and concave is if you extended the sides with their lines, right? If you drew lines through the sides, none of those lines can go inside the polygon. So if I draw a line there, and it's a little crooked, but you get the point. And then draw one there. That's terrible. Draw one there. And draw one there. None of those lines go inside the polygon, so it makes it convex. You can go around to all of those and do that, and all those lines will stay outside the polygon. The difference is, in a concave polygon, that's not the case. There would be some sides where if you drew the line through those sides, the line would go inside the polygon. Right? And so you pick any of these guys. And the arrow is as good as any, but I'm going to... Okay? The line just went inside the polygon. That's concave. Okay, they're either going to be one or the other, so if you can eliminate one of them, then you've got the description there. Okay. Another way that I've heard students use before, and I always like to talk about what students say, because that's what you guys are, right? So you guys all think the same. Right? Is that concave looks like these polygons, one of the sides has caved in. I've heard that before. Right? So this side looks like it's caved in. So that guy's concave instead of convex. Right? A couple different ways to tell. Whichever one you like, run with it. Okay? Now the definition up here says at least one segment connecting two vertices is outside the polygon. This is what they're talking about, right? If you took a segment and connected this vertex to that vertex, those are still vertices, then that segment is outside the polygon, and so that's why it's concave. It's another way to tell. Okay? You can't do that with these guys over here. All right? So, Let's identify some of this stuff real quick. Tell whether the figure is a polygon and whether it's convex or concave. That guy right there, does that count as a polygon? Anybody? Quick guess.
Yes.
No.
Oh,
It's all right. It's just quick. This is just sort of first thoughts. No. And the problem is there's a segment right here that's touching more than two other segments, and that's one of the criterion for a polygon. So this guy fails that. Okay? And we're doing this quickly, and the definitions back there in your notes, make sure you understand all the criteria. So this guy is not a polygon. Since it's not a polygon, it doesn't make a lot of sense to talk about convex or concave. Okay? What about that guy? Is that a polygon? It is. If you go back to all the criterion, all the sides are segments. They each touch exactly two other sides, and they're touching at endpoints, then we're in good shape. Convex or concave? Convex, yes. Okay. How about that guy? Is it a polygon? No. Why not?
Because it has a curve.
Okay. So then, it's not made up of three or more segments. We could say that. Okay. It's not made up of three or more segments. Okay. Well, part of the figure is not a segment. Something like that. Talk about not having a segment. All segments. Last but not least, this guy. Polygon or no? Yeah. Okay, good. Satisfies everything. Convex or concave? Concave. Okay, some of the sides are caving in. Whatever you like. Okay. Oh, am I out? Okay. Okay. So, still talking about classifying polygons. We can type them based on the number of sides. And so each polygon based on the number of sides is going to have their own special little name. And so we need to understand these names. We need to know these names, and we need to be able to talk about them and use them so that if we use the type, the name type of the polygon, that we know how many sides there are. Okay, most of these you already know. Something like a polygon with 3 sides. Hopefully you remember is called a triangle. Okay, a polygon with 4 sides. I'm sure you've heard it before. Just probably it's been a while. 4 sides. It's a quadrilateral, right? Quad meaning 4, lateral meaning side. Okay, 5 sides. It's a pentagon. Yep. 6 sides is, for any of you budding mechanics, hex bolt, hexagon. Okay. The head of a hex bolt has 6 sides to it. Okay, 7. And we're starting to get into some prefixes. We're going to pull science into this a little bit. I think chemistry does a lot of prefix work, right? So what prefix means 7? And that's heptagon. A-sided polygon. You MMA fans. It's called an octagon. That's the shape of the ring in a mixed martial arts fight. Okay. 9. 9's always a tricky one. It's always a tough one to remember. But 9, the prefix that means 9 is nana, so nonagon. 10-sided polygon is a decagon. 12-sided polygon, again, another tricky one. It's always a hard one to remember. Only it has a pretty funny name, so it becomes easier to remember if you can think about the funny name. And it's dodecagon. Okay? Now, once we get past 12 and we skip 11, and I don't know if it's because there's not a prefix that means 11, but we don't have a cute name for an 11-sided polygon. But beyond 12, so 11 and then anything beyond 12, we stop coming up with fancy names. And we just start using the number of sides in the name. So if it has n number of sides, what we'll do is we'll call that thing an n-gon. So for example, if it's got 72 sides, and polygons can definitely have 72 sides, They can have 128 sides. They can have 4,621 sides. Have as many sides as you can imagine. But if it has 72 sides, then we just simply call it a 72 gon. Okay? And stop trying to be tricky. Okay? Now, some more definitions for you. All sides are congruent in an equilateral polygon. All angles are congruent in an equiangular polygon. And then if it's both equilateral and equiangular, then we call it regular. It's a regular. And if we can get something, if we can find anything to be modeled by a regular polygon, then we actually know a lot of information about that. Okay? We'll get into regular polygons a little bit later, but they're actually very, very useful. Okay? All right. So we're still classifying. Classify the polygon by the number of sides. Tell whether the polygon is equilateral, equiangular, or regular, and then explain your reasoning. Okay? Well, this guy's got 1, 2, 3, 4, 5, 6 sides. So it's a hexagon. And if you look, all the sides have the same tick marks in them, so it's equilateral. All the angles have the same number of arcs in them, so that's equiangular. Since it's both, we do call that guy regular. So this guy is a regular hexagon. Okay? Next guy. Okay, take a couple seconds to think about it. Number of sides, then is it equilateral, equiangular, or can we call it regular because it's both? Okay, so number of sides, it's got 1, 2, 3, 4. It makes it a quadrilateral. And if you look, this side and this side do not have the same number of tick marks in them. So not all the sides are congruent to each other. These guys aren't congruent to each other. And then if you look here and here, those angles do not have the same number of arcs in them. So all the angles are not congruent to each other. So this is not equilateral or equiangular. It's neither, so we just call it a quadrilateral. All right? Another guy here. Okay? If you look, it's got, well, I'll let you think about it for a second. Okay, do you have enough time to count the sides? There's 12 sides, so this thing is a dodecagon. And if you look, all of the sides do have tick marks in them. Okay, so it's going to be equilateral, but because it's concave, and hopefully you guys understand this is concave, it's too difficult to talk about this guy being equiangular. All of the angles inside the polygon are the same. And then the angles on the outside of the polygon are all 90 degrees as well. But when we talk about equiangular, we want all of the angles inside the polygon to be the same. And technically they're not. And so without going into a lot of detail, if anytime you have a concave polygon, it's not going to be allowed to be equiangular. So we've got a dodecagon that's equilateral, but because it's not convex, it is not equiangular. Okay? So we can't call it regular. All right? All right. Some uses here. Quick, again, like I said before, if we can ever model anything using a figure from geometry, and very often we can use that information to help find side lengths, angle measures, things like that, lengths of anything and angle measures. So a table is shaped like a regular hexagon. We've got a couple of expressions that talk about to represent the side lengths of the table. Find the length of a side, okay? Well, since it's a regular hexagon, we know that all the sides are congruent. And because we know that, then that means we can take 3x plus 6 and set it equal to 4x minus 2. Okay? And then solve. Subtract 3x, add 2. This is 8. So x is 8. It wants us to find the length of a side. So we're not finished. We've got to take this 8 and plug it in. So 4 times 8 is 32. 32 minus 2. So this length is 30. You would be very wise to go ahead and check the other side to make sure that you get 30 there as well. So you plug in 8 here. Okay, 3 times 8 is 24, plus 6 is 30. So you do get 30 here, so you know you've done the problem correctly. Okay? All right. I'm going to get through the solution in the slideshow here. Okay? And that's it. Let's see. Ignore that for your homework. Your homework is posted into Canvas. So don't worry about this. The numbers may be somewhat the same, but the homework is in Canvas. Make sure you pull that down and start working on that. And we'll see you guys next time.